All right, so let's take a look at precision, accuracy, and uncertainty and how we're going to use them this year. So precision, we have two ways to think about it. We can think about it as a single point, or we can think about it as multiple points. So if it's a single point, we're really looking for how precise the number itself is. So we're looking at the sig figs, and specifically the place value, not the number of sig figs. So for instance, 1.2 and 1.20, this one goes another place value, so it's more precise. 563.4 grams versus 2.16 grams. Again, this one goes one more place value. The more place values it has, the more precise it is. Now, if you have multiple points, it changes it a little. This is talking about the consistency of the data. How consistent is it? So let's take this scale, for instance. So I'm going to take this tennis ball, I put it on the scale, and I get a measurement. Now, if I do this over and over again, am I going to keep getting the same value? Yes, that means I don't need to do many trials. Okay, you probably learned that in chemistry, that once you weigh it once, you're kind of done. Now, if I was to take this tennis ball and time how long it takes to drop it from eye level to the floor, and I try it again, am I going to get the same value? No, it's going to be less consistent. So what does that mean I need to do? I need to take more trials. So consistency or precision helps us determine how many trials we really need to take to get a good value for it. Right. Speaking of good value, that brings us to accuracy. Okay, so how correct is your value? Now, this relies on a few things. Number one, your instrument. So for instance, if I didn't zero the scale first and I measured the mass of this, would it be correct? No, because I didn't zero the scale. I'm using an inaccurate measurement. Or let's say some sneaky student snuck into my room and cut off the front of every meter stick by a couple centimeters, and I start measuring and I say, yeah, that line is 77 centimeters long. Is that line 77 centimeters long? No, okay? Or maybe someone's painted my meter stick, so I kind of don't know, and I look at it, I'm like, gosh, that's about half a meter stick? Okay, am I gonna know exactly that's a half? It looks pretty close. Maybe it, I don't know, within a couple centimeters, but that's giving me an accurate value because I'm using an actual meter stick. This one's the full meter, where this one was, I don't know, something less. It has a centimeter cut off on that end and 20 on this end, okay? So, if I don't know the value exactly, I can estimate it. So for instance, when I use this one, I said, it's about half. But I'm gonna say it's plus or minus 10 centimeters. That plus or minus, that's talking about uncertainty. Now, we are going to be using uncertainty in our labs because that helps us understand what does our percent error and our percent difference really mean. Okay, let me give you an example. So let's say I have these data points that are in green here. Okay, they're all spread out, meaning I have a low consistency, so I need more trials. Okay, so I took 5, and I found my average, which was this blue dot. Okay. And the correct value should have been this red dot. Now, they're off, so there is some percent error there because they are off. But you'll notice that that red dot, is that kind of in the realm or in the range of my green? Yeah, so that means I'm doing okay. If I wanted this average to get closer to that correct value, how could I increase that? More trials. The more trials you do, the better average you get. Now, let me give you an example of how we're going to use this with percent error. Correct value is 5 seconds, and we're going to look at group A, which had 5.2 seconds plus or minus 1 second. So they weren't using a very precise measuring tool for their time. Group B used a much more precise measuring tool, got the same answer, but had a plus or minus of 0.1 seconds. Now in both cases, we had 4% error. So you might say, hey, 4% error. That's good or not good. I don't know. You don't know. 4% error can be good, 4% error can be bad. So how we tell is we look and we say, okay, is 5 seconds inside that range of plus or minus 1 and 5.2? Yes, that means it's good. It's as good as I can do with the equipment I used. Now this other group that used a more precise measurement, is 5 seconds within inside that range? No. It is slightly outside the range, so this actually fits in our okay range, and we're going to figure out how we can determine if it's good, okay, or unacceptable. Okay, there you go.